Okay, all right, let's get started. So today's goal is to define SAT, define NP formally, and define NP completeness, and show you one non-trivial reduction from SAT to independent set. Okay, so that's the agenda. Just to recap, when we think of what is a polynomial time reduction from problem x to problem y, here x and y are decision problems, right? And we write it as x less than equal to py, which means x should be easier than y. Why is it easier than y? Because we are able to transform x into an instance of y, right? Transform x into y so that we can use an algorithm for y to solve x, right? That's the idea of a reduction, that when you reduce x to y, we are saying, we can, if you had an algorithm for y, we can solve x. So that means that somehow x is easier than y, right? Okay, that makes sense, right? Okay, and why we have to care about the efficiency of the reduction. What does it mean, the efficiency of the reduction? Well, how long does the algorithm to convert an instance of x into an instance of y take? That should be efficient. If that is not efficient, then we can solve the problem x by itself by doing something brute force, right? So here that doesn't make sense. So the reason to care about polynomial time reductions is that if x reduces to y in polynomial time, then a polynomial time algorithm for y implies a polynomial time algorithm for x, right? And we are looking at a very specific type of reduction which looks like this, right? It's called a Karp reduction. What does it do? It just does a very simple thing. It takes an instance of x, converts it into an instance of y, and just asks for the answer from the algorithm for y. If it is yes, it will say yes. If it is say no, it says no. That's a very simple kind of reduction called a Karp reduction. In general, we can have what's called a Turing reduction. What is a Turing reduction? Basically, it is just a subroutine, and you can call it any number of times you want, not once, right? You can do whatever you want with it, but you need to, right? So this is something that we use in algorithms normally, because why should we restrict ourselves to using the algorithm for y only once? We can maybe use it 10 times, right? Well, this is something that is more useful for proving hardness kind of results, right? And we'll see when we come back to the asymmetry of NP why that's important. Okay? There is an example and some more background that I'll let you read. So now let me define this problem SAT for you, right? Most of you have probably heard of the problem SAT. Who has not heard of SAT, just to get a sense? Has everyone heard of the problem SAT? But in any case, let's recap. What is SAT? SAT is a problem, right? What is it? It's a logical problem, satisfiability. So the input consists of n Boolean variables, x1, x2, xn, and some m clauses, right, which are in a very specific form. They're called conjunctive normal form. All that means is that there are of many literals, right? Okay, so we have n Boolean variables, but the variables can occur either in two forms, as xi or not xi. So we call them literals instead of variables, right? So we distinguish variables which are x1, x2, xn, which can take 0, 1 values, true or false, from the literals which are either in the xi or not xi. Okay, and a clause is simply a or of these literals, some number of literals, right? So a clause of this form is x1 or x2 or not x4 is a clause, right? Sometimes you put bar on top, sometimes you put explicitly not, depends on the notation, right? A formula in conjunctive normal form is simply an and of a collection of clauses, right? So here we have 3 clauses over 5 variables. x1 or x2 or not x4 is one clause, x2 or not x3 is another clause, x5 is not x5. Sometimes we explicitly write and, sometimes we just list them with the implicit understanding that we want to satisfy all these clauses, right? It's an and. So this is called CNF formula, and a special case of this is a SAT problem, right? What is a SAT problem? Well, I give you a formula like this and I ask, is it satisfiable? What does it mean? That can I assign zeros and ones or true or false to the variables such that this formula is satisfiable? How can you satisfy a formula? Well, this is an and of clauses, so all the clauses have to be true. How can a clause be true? Because it's an OR of literals. You can satisfy it by setting at least one literal to true. Setting a literal to true means that it depends on whether the literal is in the regular form or in the negated form, right? So, if you set x2 to true, this clause will be satisfied because it's an OR. But you can set x4 to false, and that also will set this clause to true, right? So that's what it means to satisfy this formula, right? It's a special case of Boolean formulas. And okay, so what is 3CNF formula? A 3CNF formula is a formula in which all the clauses have exactly 3 literals. Okay, it can be a KCNF in general. It could be 2CNF, it will be 5CNF, it will be 10CNF, right? When we say that, it's exactly K, okay? And moreover, we insist that you cannot duplicate, you cannot have 2 literals which are 2 variables, 2 literals, identical literals in the same clause. So when we say 3CNF, you can't say, I have x1 or x1 or x1. We don't allow that, okay? Right? We need to have them, the variables in the literals have to be distinct, okay? Okay. So clearly 3CNF formulas are a special case of CNF formulas, right? Yeah? I mean, we are making an additional restriction. So what is the satisfiability problem? SAT for short. I give you a formula and I say, is this formula satisfiable? Okay? That's it, as simple as that, right? It's in this restricted form, in this conjunctive normal form, right? And of several clauses, each of which is an OR of several literals. Okay? So typically we use n to denote the number of variables and m to denote the number of clauses. Just like in graphs, we use n to denote number of vertices and m to denote the number of edges typically. If I forget, n is the number of variables typically and m is the number of clauses. Okay, both are part of the input. Okay. Okay, what is 3SAT? 3SAT is the same problem except that I only give you 3CNF formulas. Okay, it's obviously a special case of SAT, right? Okay, these are simple problems, these are easy decision problems, right? You just have to decide yes or no, okay? Is it formula satisfiable or not satisfiable? Okay, now, here is an example of a formula that is satisfiable, right? Why is it easily satisfiable? We can set all of them to be true, in which case this clause is true, this clause is true, and this clause is true. Right? There are many ways to satisfy this. Here is an example of a formula that is not satisfiable. Right? Why is this formula not satisfiable? Intuitively, what is going on here? All possible clauses I gave you with those two variables. So whatever assignment you pick, right, there is one clause which won't be satisfied, right? Right? So clearly this formula is not satisfiable. This is not the only reason why formulas are not satisfiable. There can be complicated reasons why formulas are not satisfiable, right? Okay. Okay. So now these are SAT and 3SAT, they're very important problems. Why are they important problems? Well, because logic underlies everything we do, right? Reasoning is what we do, right? All our activities basically proofs are reasoning from axioms to theorems, right? Okay, of course we use powerful logic for all, there exists, and more complicated forms of logic to derive most of our theorems, but propositional logic, where we just have basic axioms and then we can derive using simple implications, is already very powerful, right? So these are fundamental sort of problems, and in that sense, just like linear programming we saw is a very powerful problem, right? Why is it very powerful? Because it is able to express constraints, right? It's almost a meta problem, right? It's a language. It's not just a simple concrete problem. It almost has a feeling of a modeling problem, right? A language almost, right? So you can express many problems in the language of linear programming or integer programming, right? SAT and 3SAT is not so clear, but SAT is similarly has the feeling that, okay, it is a modeling language. We can express using Boolean constraints as opposed to real valued constraints like linear programming and stuff, right? So SAT and 3SAT are you can imagine, are expressive languages, and that's why, in fact, all our computers are built of circuits, right, which are essentially logical gates, right? So really it's powerful, and it is not surprising that it is not easy to solve, and we'll see why come back to it later on. So it's easy to see that 3 sat reduces to sat in polynomial time because it's a special case, right? You don't have to do anything, right? 3 sat is okay. What is not so obvious is sat also reduces to 3 sat in polynomial time. So what does it mean that 3 sat is as powerful as sat in some sense, right? So the restriction of having only 3 variables per clause, 3 literals per clause is not such a big restriction. In what sense? That if I give you any sat formula, I can convert it into a 3 sat formula, which is not too much bigger than that, such that the sat formula is satisfiable if and only that 3 sat formula is satisfiable. Okay? So this is not completely obvious, right? Why is the case that I can always convert a sat formula into a 3 sat formula, such that this initial sat formula phi is satisfiable if and only the 3 sat formula phi prime is satisfiable. Okay, so so how do we do this? Well, why is a formula not a 3 sat formula? If it is already in 3 sat form, we are done, right? We just say okay, right? So to reduce sat to 3 sat, what should I do? What I should do is I should give an algorithm that, given an arbitrary sat formula, spits out a 3 sat formula, right? Such that if this initial 3 sat formula is satisfiable if and only the new 3 sat formula is satisfiable. Okay, how do I do that? I'm not going to go through the proof because I do it in 374 and it's something that is not very hard and I have other things to cover, so I'm going to skip this proof, and if you haven't seen this before, you should read the notes. Okay, but the idea is very simple at some level, right? So suppose this is I'll just kind of hand wave and sketch. Suppose you look, this is why is this not in 3 sat form, right? It has some clauses are very long and some clauses are very short, right? I mean, very short means they're less than 3, right? So the idea is, if you have a short clause which is 1 or size 2, you can introduce new variables to make it a few new variables and make clauses of size 3, a collection, not one but several of them. Somehow that's such that, if this clause is satisfied if and only if all those clauses are satisfied. So by introducing new variables, okay? Alright, that's one idea. That is, you can convert short clauses into clauses of length exactly 3. Okay? The other idea is, if you have a long clause, you have to break it up into shorter clauses. Okay? That also you can do by saying, okay, suppose I have a long clause, I can break up into these 2 plus 1 a variable and 1 variable plus these things. Okay? This is a standard trick. I won't go into that. You have to look at the notes for the proof. Okay? So simple transformation. If you've not seen this, I recommend that you go through the proof carefully. Okay? If you have seen it, well, it's a review anyway. Okay? It's also, probably many of you have not been playing with logic gates and propositional formulas recently, right? So it's a kind of a good way to review why that can be done. Okay? Instead of me kind of going through it quickly, it's better for you to read it. Okay? Okay. So this is a high-level idea. It's easy to convert a sat formula into 3 sat formula. Then you say, why did you go to 3 sat? Why can't you go to 2 sat? Right? So maybe 2 sat is also possible, and then it's even better, right? It turns out you can't do it, right? Why is it? Well, maybe there is, right? But then you would prove P not equal, P equal to NP. Why? Because 2 sat we can solve in polynomial time. Okay? 2 sat, if all the clauses are of length less than or equal to 2, you can solve it in polynomial time. It's not obvious. It's a very clever algorithm. Okay? And it uses some graph theory, strong connected components, and logic and stuff like that. If you have never seen it, I recommend you read this algorithm also. It's actually, it's an exercise in Dasgupta et al. Or Klein-Buktadosh. Usually once you see graphs and strong connected components, you can solve this problem. But it's not easy. You have to know how to think about it, right? But you can do it. So 2 sat is easy. So 3 sat is somehow not so easy. Well, you can also see it from the reduction from sat to 3 sat. Why you need at least 3 literals to actually convert a big sat formula into just 3 sat formula. You can't go to 2. Okay, it won't work. Okay. Okay. So 2 sat is easy. 3 sat is hard. Okay. Okay. You can look in the books and stuff. Okay. Now let's look at. I'm going to do one very clever reduction that Karp did in 1972 or around that time. It's natural to somehow imagine that an expressive problem such as SAT is hard, right? It's a difficult problem, or at least you will have the sense that, look, if I can solve SAT, I can solve many other problems because I can express most of my problems in SAT, right? Because it's like saying, I can write a program for many of the things I want, right? Okay, but what about the other way, right? The other way is not obvious, right? Oh God, don't tell me it's going to... this stupid Windows thing. Okay, we'll see how it goes. What we will see is that concrete problems that we want to solve, like independent set, right? What is an independent set problem? A graph and a integer k, right? Is there an independent set of size at least k in a graph? That seems like a much less general problem than satisfiability. But what we'll see is that, if you can solve independent set, you can solve SAT, right? So it's a very simple reduction, very clever reduction. What does it demonstrate? It demonstrates that SAT, which looks very logical, and independent set, which looks like a very different graph theoretic problem, are essentially can solve each other. Okay, and that's a phenomenon that is very common and important to understand, because it's saying that you can capture logic and very general purpose things using some very concrete problems. Okay, and that is that's what we'll do, right? So what we're going to show is that 3-SAT reduces in polynomial time to independent set. So if you can solve independent set, you can solve 3-SAT, okay, or SAT in general, because SAT reduces to 3-SAT, right? In fact, the reduction works also for SAT, but it's easier to see it for 3-SAT because things are simpler, right? Okay, so how do we convert 3-SAT to a graph problem? It seems a little tough, but graphs are very powerful, right? So what does it mean to reduce it, right? Let's first think, what should I do? What should the reduction do? The reduction should take a formula, 3-SAT formula phi, and what should it output? It should output a graph, right, and an integer k, such that this formula, initial formula phi, is satisfiable if and only that graph g phi has an independent set of size at least k. Why? Because then I can use an algorithm for independent set and then solve my satisfiability problem, right? Right? Okay. So the question is, how do we convert a formula into a graph such that independent sets? So we should also think, what does it mean? That seems a little strange to do that, right? Because how can we convert? How do we know that this formula is satisfiable if the graph has an independent set? Okay, it means the reduction also has to tell us how to convert an independent set into a satisfying assignment, right? Ultimately, how do we prove that the reduction is correct, right? If you stop and think, why, at the high level, we have to say, if I'm going to solve SAT using independent set, okay, what does it mean is that if I have an algorithm for independent set, I should be able to solve SAT, right? Okay, so my reduction is going to take formula and give out a graph, right? Now I'm going to use my algorithm for the independent set and get an independent set, right? Okay, from that I have to conclude that the formula is satisfiable, right? But in fact, what we need to know is that not only can we decide, but we also need a solution basically. The independent set in the graph should tell me how to make the formula satisfiable. That's what the proof will do, okay? So that's important to understand, and we'll come to that, okay? Okay, all right. So first, let's first think about what does it mean to decide that, to figure out whether a 3-SAT formula is satisfiable, okay? There are two ways of thinking about it, right? And these both are, the alternate way is more important for this kind of reduction. When I think of SAT as a formula is satisfiable or not, what do I think about it? I want to think about assigning true and false to variables to make sure that every clause has at least one literal which is true, right? What is a different way of thinking about satisfying a formula, like a 3-SAT formula? I say for every clause I specify which literal is going to be true. Okay? So, this guy is going to satisfy this clause, in this clause, that guy is going to satisfy in this clause, and for every clause, I point out one literal in that clause and say that is the one who is going to satisfy it. Okay. But then what should I make sure about that? I should make sure that if I chose x5 in clause 1, I don't choose not x5 in clause 10, right? Because if I want to satisfy x5 clause 1 using x5, that means I have to set it to true. But if I choose not x5 in clause 10, I can't choose both x5 and not x5 to be true, right? Okay. So another way of thinking about satisfying a formula is for every clause pick one literal and make sure those that I don't pick a literal and its negation at any point. That's a different way of figuring out how to satisfy a formula, right? So that is another view that we'll use in the reduction. That's why I'm saying, you know, they're equivalent, right? Is that clear? Okay. Okay. So let's go to that reduction now. So pick a literal from each clause and find a truth assignment to make all of them true. And we'll fail if we pick xi and not xi, right? For any I. So we should make sure we avoid that. Okay? All right. So here is this very simple but beautiful reduction, right? So I give you a three-sort formula. Here is a three-sort formula. Not x1 or x2 or x3 and x1 or not x2 or x3 and right. Okay? This is the formula. Okay. How many variables are there? N variables, and here how many variables are there? 4 variables and 3 clauses. It's a very simple thing. I'm using an example to show the construction, right? Okay. For every clause you create a 3 vertices. So you have a box for each clause, right? With 3 vertices. Okay. So I label the vertices, right? This one is not x1, x2, x3. So I create 3 vertices, right? And I create a triangle on them. So I add those edges, right? So for every clause I create a triangle. Yeah? Well, because there are 3, right? 3 literals. Yeah? And I put names on them, right? You know, this guy is not x1, this guy is x2, this guy is x3, right? Alright? Okay? I just put a label on them. Clear? So far so good? Okay. This is easy to do, right? Okay? And then what I do is I add some extra edges. What are the edges? I put, if this guy is labeled x2 and that guy is labeled like not x2, I put an edge between them. Okay, for every pair of literals which are in conflict with each other, I put an edge between them. Okay, so not x1 and x1. What is it saying? That I can't pick this guy and that guy together, right? Because that will create problems for me. Okay, okay, that's it. That's the construction. Is the construction clear? Right? So I give you a formula, I can create this graph, right? Easy to create this graph in polynomial time from the formula. If I write down the formula, I can write down this graph very easily, right, in polynomial time. Right? Agree with that? Okay, now I haven't told you what the number I gave you, right? The independent set problem is a decision problem here. I have to give a graph and what? Some number, right? So the number I give you is m, where m is a number of clauses in the clause. Number of clauses in the formula, right? Okay. So given a formula, I convert it into a graph like this, and I also say m is the number of vertices that I think will, right? So okay. So my claim is this formula phi is satisfiable if and only if this graph has an independent set of size at least m. Okay. Okay. So let me convince you, right? I have to convince you of 2 directions. Okay. What are the 2 directions? If the formula is satisfiable, the graph has an independent set of size at least m. If the graph has a independent set of size at least m, then the formula is satisfiable. Okay, they're different. Okay, their proof for them is not the same. Okay, it's very important to realize that you have to prove 2 things, right? When you prove a reduction is correct, you have to prove both things. Is that clear? Otherwise, we don't not proving the correctness of the reduction. Okay. Is it intuitive that why we need to argue both ways? Or no? Yeah? Okay. Alright. So how do I convince you? Okay, k is the number of clauses. Okay. So if the formula is satisfiable, I want to claim that there is an independent set of size m, right? Okay, intuitively what is going on? I want to claim that I can pick one vertex from each triangle and I'll get m vertices, right? That's what I want to prove. Okay. Okay. So clearly I can't pick more than one vertex from each triangle, right, in my independent set, because they are all connected to each other. Okay, so why can I pick m vertices if the formula is satisfiable? Okay, what does it mean the formula is satisfiable? That means for every clause there is at least one, I mean there is an assignment, right? There is a truth assignment which I may not know, right? There is a truth assignment such that in every clause at least one literal is true, right? Okay, so think of a truth assignment for this. Give me a truth assignment for this formula. Say, pick an assignment for me. So maybe I'll choose this as false, x2 as false, and x3 as true, yeah, and x4 as what? Whatever, right? Well, okay, no, but I see, instead of thinking about it like this, what I want to think is there is an assignment, and pick any true guy in this, fix that assignment, right? And in this clause there must be at least one true guy, right? Say, it's x2, pick that vertex, okay? And, okay, so let's pick arbitrarily, fix an assignment. What is an assignment you'd like to pick? Let's say, x1 is 0, x2 is what? 0, x3 is 1, x4 is 1, right? Say, that's an assignment which, satisfies this. What does it mean? It means in this clause, what are all the true literals? This one, and in this clause, what is true? This one, and in this clause, this one, and this one, right? So pick arbitrarily one guy from each clause. Okay, so here, maybe I'll put x3, right, and say, this is the vertex I'll pick. And here, I don't care, x2 I'll pick, and x1 I'll pick, okay? I claim that's an independent set. Why is it an independent set? Why is it not an independent set? If it's not an independent set, it means that two of them should have an edge between them, right? Yeah? But how can there be an edge between two of the ones I picked? There can be an edge if and only if, by construction, if I have an edge, that means that one of them is not and one of them is a variable and one of them is a not of that variable, right? But how can a fixed truth assignment have true for both of them? It cannot, right? So no two of the ones I picked can have an edge between them in my construction. So those vertices will be independent, right? And also I didn't pick more than one from triangle, right? That's also true. I only picked one from each triangle, so they can't be in. That's also fine, right? Is that clear? Yes, questions? So if there is a satisfying assignment to the formula, I can give you one independent set of size at least m, right? Where m is the number of clauses. Yeah? Questions? Yeah? Okay, now I have to prove the converse, which is usually the difficult direction. Okay? What does it mean? That if the graph has an independent set of size m, then I have to prove that there is a satisfying assignment to the formula. Okay? How do I prove that? Okay? Okay. I mean, here I'm using k to be the m, right? Number of clauses. So, how can there be so let's look at the graph. How can there be an independent set of size m in the graph I constructed? Remember, it has m triangles, right? If there is an independent set of size m, then it must be that every triangle has to have one vertex, right? Because I can't take two from each triangle, right? So every triangle has exactly one vertex in my independent set, right? Because there are m triangles and I have an independent set of size m, right? So each of the triangles has one vertex in my independent set. I claim that I will pick that literal to be the one which will satisfy the clause. Okay, what does it mean? Look at that vertex. That vertex corresponds to a literal, right? So, So, if you give me an independent set, if you say, you picked x2, then I'll say, my truth assignment is x2 will be true. Okay? I walk from triangle to triangle, and I say, oh, you pick this vertex in the independent set in this triangle, so I'll make that literal true. Okay? So I'm giving you an assignment, right? Why would I not get a truth assignment? At some place I get stuck, right? What does it mean at some place I get stuck? I come to a vertex and I want to make it to a label, literal, and say I have to make it true. Oh, wait a second, I already made it false somewhere else, right? Then I can't make it, I don't have a truth assignment, I'm stuck. But how could I have picked false? That there would have been an edge between the two of us, right? So I could not have picked it previously, right? So it wouldn't have been an independent set. Okay? So given an independent set of size m, I gave you a way to construct an assignment to the formula which satisfies all the clauses, right? So it means that if there is an independent set of size m, then there must be a satisfying assignment to the formula. Okay? Questions? Do you believe it? I don't know. Yeah. Isn't it clever? Yeah. No? See, too easy. Yeah. It's simple, not hard, no? But it's not hard. But it's clever. Okay. Okay. So, okay. So that's it, right? All right. Okay. But this is the power of reductions, right? Okay. Now we'll play with transitivity, right? Okay, that's the power of reductions. X less than equal to y and y less than equal to z means x less than equal to z, right? Okay, and we already saw this, right? Remember we reduced independent set to vertex cover. Okay, so we can reduce SAT. We saw just reduce SAT to independent set. Now we can reduce SAT to vertex cover, even though a direct reduction to vertex cover doesn't look so obvious. Okay. So the transitivity of reductions is there. You can create these long chains of reductions, right? Okay. What is the power of these long chains of reductions? That you can pick a problem which is close enough to your problem rather than something which is far away, right? Close enough in the sense of some similarity, right? So if you already know a problem which is sort of similar to what you know, then it's easier to do the reduction than something which looks a little tricky like this one, right? Okay. So that's the power of reductions. Okay, so now let me define NP for you formally. And so we saw several problems: independent set, vertex cover, set cover, SAT, 3-SAT, and we saw that we just saw this reduction, and we also saw that independent set reduces to vertex cover and vertex cover reduces to independent set, right? And we saw that vertex cover is a special case of set cover, right? It's a special case of set cover, and we saw SAT and 3-SAT are equivalent. Okay, those are the things we saw. Okay, we'll skip this, right? So what is our notion of efficiency? I think I stated it earlier on that we think of polynomial time as efficiency, right? Okay, so P is a class of all problems that can be solved in polynomial time. Here we restrict our attention to decision problems for simplicity, right? Otherwise it's a little trickier, right? To define formally optimization problems and stuff. So P is a class of all decision problems that have solved it in polynomial time, that can be solved in polynomial time, right? So this is the class we are interested in, or we like P, right? So there are many nice problems in P, right? Shortest paths, max flow, min cut, right? Some obvious, some not so obvious, right? Like min cut is not obvious, right? Okay, but these ones, we don't know any polynomial time algorithm. Okay, we don't have a polynomial time algorithm for independent set, vertex cover, set cover, SAT, or 3-SAT. Okay, these are very nice problems. If you could solve them, we could do a lot of funky things, right? We know how to solve them, right? So why is that, right? What should we do when we don't know how to solve them in polynomial time? We don't have any efficient algorithm. It could be that we are simply not clever enough, right? Or maybe there is no polynomial time algorithm for them, right? That is also a possibility we have to entertain, right? So we would like to prove, right? And as mathematical people, we can't just simply say, oh, well, we should try, right? To prove, is it true that there is no polynomial time algorithm, or is it just that we're not clever enough, right? Because algorithms can be tricky. Okay, so well, we have failed, so we'll do next best thing, right? When you fail, you kind of say, okay, maybe we should do something at least which reduces some ad hoc nature of thinking about problems into a more systematic way of thinking about problems. So how is it, what is one thing you could try, right? One thing you could try is that, is there anything common about all these problems that we can think about in a unified fashion, rather than, oh, vertex cover I don't know how to solve, independent set I don't know how to solve, 3-sat is different. Is there something common? And this is the field of computational complexity. Okay, the field of computational complexity is like, how can I understand problems not individually but in a more structured way, in a classical, I mean, how can I classify problems into similar problems, right? Okay, and so you say, is there something similar about these problems? Why are we stuck on all these problems? And then people notice that all these problems have this very simple feature that is very natural for us, right? As human beings, it's very natural for us. They have the following feature, that it's like our homework problems, right? Or our exam problems. They have the feature that it's very hard to find the solution, but if I tell you the solution, you'll say, that was so easy, right? Okay, so what does it mean, right? Formally, is that these problems have the feature that if I give you a solution to them, it's easy to check that it is a solution. Okay? Okay, so what does it mean concretely? If I give you a formula and I want to convince you that it is satisfiable, how can I do it, right? I can give you a satisfying assignment, right? And you can verify very easily that, yes, of course this satisfies the formula. Yeah? So if I want to convince you that a given graph has an independent set of size at least 2000, what can I do to convince you? I can give you the independent set, no? Look, this vertex, this vertex, this vertex, this vertex, this vertex is the independent set. And what can you do? You can say, I'll look, yes, of course that's an independent set, it has size at least 2000, right? Okay? It's the same with homework, no? If I give you the solution, you can check that that solution is correct for your problem, right? But coming up with the solution yourself is hard, right? It may be hard, I don't know, right? It depends on the problem, right? Okay, so that seems like, that's such a trivial property. Why, you may say, that is so obvious that every problem should have it, you may think, right? But it's not true, right? And so formally, the problems, the NP is the set of all problems for which, if the problem is what's called a yes instance, that means that it is in fact a yes, what is a yes instance, right? A yes instance is that, remember, we are in decision problems, right? Decision problems means that every instance has either answer is yes or no, right? So the way to think about it is, look at our SAT. What is SAT? SAT is basically all formulas. Think of it as all formulas, right? And some of them are satisfiable, some of them are not satisfiable, right? And our goal is to find an algorithm which, given a formula, will say yes or no, right? Okay. Now, NP is a little tricky for precisely this subtle reason, which is glossed over, right? But NP is a little tricky to understand because it has some asymmetry built into it. Okay, and I want us to think about it a little bit slowly. Okay, so NP is a set of all problems which have the following feature. If the instance is a yes instance, then there is a short proof I can give you. Short is what? Polynomial in the length of the instance. And there is a polynomial time algorithm, efficient algorithm, which can verify that that proof satisfies that instance. Okay? Think SAT. Okay. What is your verifier? Okay? Your verifier is simply going to take an assignment and check that each clause is satisfied by that assignment, right? Okay? So, okay. So what I'm saying is, for SAT, ideally what would we like? We would like an algorithm which, given a formula, and efficiently says yes or no, right? Well, we don't know if there is such a thing exists or not. Okay? But I'm claiming that it has the following feature. I can give you a polynomial time algorithm, okay, an efficient algorithm, with the following property. If you give me a formula and an assignment, it can check whether the assignment satisfies the formula or not. Right? We all agree on that? There is such a simple, efficient algorithm. Okay? Now clearly, if a problem is in P, it doesn't need this extra information, right? It can just solve it itself. It doesn't need any extra information. It will just do it efficiently and say, yes or no, right? But the next best thing is what? This is what is, at least this is a simpler property, right? That I have an efficient algorithm that is not going to solve the problem, but at least if you give me a solution, you can check it, right? So a problem is in NP if there is an algorithm, efficient algorithm, polynomial time algorithm, with the property that for every S instance, there is a proof which is of not too long length that can convince that verifier. Okay. Moreover, it should be the case that if the formula is not satisfiable, whatever you give, the verifier won't be satisfied. Otherwise, it's dumb, right? Okay. So what does that mean? If I give you a formula and the formula is not satisfiable, okay, your algorithm should not be fooled by a false assignment. Okay. Okay. Your verification will fail, right? If you give it an assignment which is not satisfying it won't agree to it, right? It's a minimal basic sanity check, right? So a problem is in NP if it has a minimal basic sanity checking verifier, okay? Yeah? Okay? All right. Okay, so more formally, okay, more formally is just to make sure that I'm not skipping anything for you, right? Okay. A decision problem we'll talk about it, see, NP has two definitions. Some of you probably have seen it via non-deterministic polynomial time using Turing machines, right? Most of you probably have forgotten Turing machines, right? And what is non-determinism, right? It's hard to remember all that. It comes from, that's why it's called NP, non-deterministic polynomial time, coming from Turing machines, right? But this is a definition which doesn't appeal to Turing machines and is much more intuitive, okay? So, but it makes some things hard. So, okay, so let me define what's called a certifier. An algorithm for a problem is called a certifier if it has the following properties, right? It takes two inputs, okay? The first input is what? The input to the original problem, x, right? Think of SAT. What is the input to the SAT? It's a formula, right? And what is the second input? The second input is what is called, I'll call a proof, another string, okay? And it has the following property, that if that input is actually a yes instance, there exists a proof such that the verifier will say yes, okay? Okay, think of this as your verifier for SAT. If the formula is satisfiable, there exists an assignment which will convince the verifier, right? Because if you give it the right one, it will check and say yes, right? Moreover, if the input is not a yes instance, that means it's a no instance. If the formula is not satisfiable, then the verifier will not say yes to any input, any proof you give it. Okay? You cannot fool it by convincing it for a formula which is not satisfiable. Okay? Is that clear? Okay? It's called an efficient verifier if it has the following feature, that it runs in polynomial time. Okay? The algorithm runs, the certifier itself runs in polynomial time. And the second property is also important, that the proof length is of size polynomial in the input length of the instance. Okay, this will become more concrete in an example. Okay, it's maybe a little abstract now, right? So let's just do quick examples. What about independent set? Are you convinced that independent set has such a verifier? So what is the input to an independent set? It's a graph and an integer. And what is a yes instance of independent set? All pairs gk such that G has an independent set of size at least k, right? Now, if I give you gk and it's a yes instance, what is your verifier? Verifier expects what? It expects an independent set, right? You can create an algorithm which says, to convince me, give me an independent set, right? So what does it do? It looks at the independent set you give and it will check, it's a subset of the vertices, right? And it will check whether first the number of vertices is at least k, And second, that they actually form an independent set in the graph. Why? By taking all pairs and checking if there is an edge in the graph or not, right? If there is any edge, it says, sorry, you are trying to fool me, right? If everything succeeds, it will say, yes, you convinced me that, right? It's very easy, right? It's easy. Okay. Okay, same thing for all the problems you can think of, simple problems, right? It is true. You will say, why isn't every problem in NP? That's something that, okay, let me try to give you one example where, this property is not obvious for all problems. Suppose my language is composites. That is what it means. I want to know whether a number is composite or not. Okay? How will you convince me that a number is composite? Okay, maybe there's a polynomial time algorithm. Do you know if there's a polynomial time algorithm? For checking whether a number is prime or composite? It's a very basic problem, no? Given a number, is it prime or not, right? Okay, it is in polynomial time, but it's a very non-trivial algorithm, okay? It's not easy, okay? But anyway, let's not worry about it. Let's say, we don't even know it's polynomial time, right? Actually, you guys don't know whether it's in polynomial time. So let's see, is it in NP? What does it mean to be in NP? That means that, can I at least verify that a number is, can I check, if somebody is trying to convince me, can I check whether a number is composite? How will I check? What should my algorithm to check be? What should you give me to convince me that a number is composite? No, I don't want, remember, I'm not trying to find an algorithm, right? I just want to decide, you need to convince me. How can you convince me the number is composite? Yeah?
Just some number that's not one for itself. Check to see if it's divisible,
Right,
right?
you can convince me by giving a factor, right? If I want to check, I can, if you want me to check everything, then, that is not a polynomial time, because that's exponential time. If you try all factors, that's exponential time in the input length, because the input length is only log n bits. Okay? But I have the following thing, right? You give me a factor, I can check and see whether it's actually a factor of the number, right? By just doing division. Right? Or you can give me two things. In fact, you can make my life even better, right? What can you give me? You can give me a factorization even. Then I don't even have to do division, I can do multiplication, right? Yeah? Okay? Okay. So composite is in NP, right? Okay. But NP is a little tricky. Why? What is not composite? Prime, right? What is not composite is a set of all prime numbers. Okay, now you have convinced me that a number is prime. How will you convince me the number is prime? I give you like a 200-digit number, right? And I say this is prime number. Okay, and you're like, oh, whoa, wait a second, what am I going to do now, right? How can you, remember, in all your RSA security is based on prime numbers. Okay, what does it mean, right? That, I come to you and say, look, use this because it's a prime number, right? And you're like, oh, this is 200 digits. How am I going to check whether it's a prime number or not? Remember, your number of digits in your SSH and all these things are like 128 bits, 256 bits, right? You can easily write it down because it's only 256, it's a small file, right? But how will you check it's a prime number, right? Okay, or rather, so checking whether it's a prime, we don't even, it's hard to think of an efficient algorithm for it. But I'm not even asking to check whether it's an efficient algorithm. I'm just trying to say, can you even convince me it's a prime number by giving me some proof, right? So that is asymmetry in NP. Remember, composite is easily in NP, right? Why? Because I can convince you that a number is composite by giving you a factor easily. And you can check. But the complement is composite is what? Prime, right? So it's not, actually, NP is not closed under complement. Okay? That is, take a formula. Suppose I want to convince you it is satisfiable. I can give you an assignment and you can convince yourself that it is satisfiable. How can I convince you a formula is not satisfiable? That's very hard, no? If I try all, trying all possible assignments is the same thing as me trying enumeration, right? That's not efficient, right? Okay, so NP is a bit subtle in its definition because of this asymmetry that it's only, the certifier is only going to be able to certify yes instances, not no instances. Okay? It's a tricky notion. Okay? But many problems that we care about turn out to be, so you may say, there is a notion of co-NP. Okay? And I'll briefly discuss it next week, but just be aware that the NP is only for yes instances, okay? And the certifier is only supposed to work, the proof should exist only for yes instances, not necessarily no instances. Okay? Okay. Just to give another example, right? One more important aspect of the NP is something that, is easy to miss, is the following, right? Remember, what does the certifier take? It takes the input instance and a proof, right? Normally we think, how can the proof be longer than the size of the input itself, right? You may say, oh yeah, how can the if I give you a formula, what is the length of the satisfying assignment? It's only 1 bit per variable, right? It's not very long, right? But not every problem is immediately obvious that the proof certificate is actually going to be short. Okay, so here is an example. It looks like a very innocuous problem. Okay, it looks very simple. Here are two strings, right? What is this problem? It's called PCP. Okay, right? What is the input to the problem? I give you two sets of binary strings. Okay, alpha 1 alpha up to n and beta 1 beta n. Two sets of binary strings. Okay, that's of some length. Okay, there could be 100. Arbitrary length, but that's the input. Right? Two sets of strings. Okay? Agreed? Okay. And you have to decide if the following is true. There are different lengths and different strings, right? Can I take these strings and use multiple copies and concatenate them so that I get two equal strings? Okay? Okay. So I wish I had a good example, but in interest of time, I won't do this. So what does this mean? Is the problem clear, or what do I want to do? I take the alpha 1 alpha 2 alpha n, beta 1 beta n. There are two sets of strings, right? I want to jumble them up in any order you want, right? So that when I concatenate them, I get with the additional constraint of the following, right? If I take alpha 1 here, I have to take beta 1 here. If I take alpha 2 here, I have to take beta 2 here. Okay? Or if I take alpha 10 here, I have to take beta 10 here. Okay? There is a correspondence. That is, whenever you take the ith string of these guys, you have to take the ith string of the other set. Okay? You can take any number of copies. Okay? But at the end, I have to get equal strings when I concatenate. Okay, this is like a strange problem, right? Okay, okay. My claim is, suppose there exists a solution, right? I can convince you easily, right? How? I tell you, oh, these are the set of indices. First put alpha 1, then put alpha 2, then put alpha 10, right? If you give me the sequence of the indices, I can concatenate the strings and verify that they are equal, right? Yes? Okay, then you say, no, this problem is an NP. Okay, right? Because I have an efficient verifier, right? Okay, there's a catch. What's the catch? There's a second part of NP which we usually ignore because it's so obvious in most problems. But I want to highlight this, right? If there is a solution, you also need the property that the length of the solution is polynomial in the length of the original input. Okay? You have no idea of, given this problem, how long this sequence has to be as a function of the original input. Okay, you have to prove that this problem is an NP, you have to convince yourself that if there exists a solution, there exists a short solution. Right? What does short mean? Is it clear that if I give you, like, say 100 strings and 100 strings, there is always a solution, if there is one, such that the length of the sequence should be only polynomial in that 100, or the initial input? You don't know that, no? See, for a formula, how do you convince me that it is satisfiable? By giving me a satisfying assignment. But the length of the satisfying assignment is very short, right? It is no more than the number of variables, right? Okay, that is very important too in classifying a problem as an NP. Okay, if I give an independent set problem, to convince me, you just have to give me an independent set, right? But how long do I need to specify the length of the independent set? I just have to give you n indices, right? This guy is an independent in my set, this guy is my set, that is not in my set, this guy is my set, right? So not only can I efficiently verify if you give me a solution, the length of the certificate or proof is polynomial in the size of the initial graph, right? Well, for this problem it is not obvious, right? Unless, how do you know? You have no idea, right? Okay? That there should always exist a short solution, right? So in fact, this is called the post correspondence problem, and it's an undecidable problem. There is not an algorithm, forget efficiency. It's not even a decidable problem, okay? What does it mean? That means there is no bound on the necessary length of the feasibility of the solution, even if there exists a solution, okay? So that is the second part of the NP that you have to be careful about, okay? It's not enough that there is an efficient certifier. The length of the proof also has to be polynomial in the input length. Okay? Okay, just to give you a simpler example, take not sat. What is not sat? All the formulas that are not satisfiable. Here is my proof. My proof is the string of all the assignments, right? And you can check that none of the assignments satisfy the formula, right? That's easy verification, right? But that's not a efficient thing, right? You know, because your length of the proof is exponential in the size of the formula. I can do it myself, right? Why do I need your proof, right? So that's the important part of NP2, right? Pay attention to that. Okay. Non-determinate. This asymmetry on this is important. Okay. So now let me make some simple observation. P is a subset of NP. What does it mean? Every problem in P is also in NP. Why is that? Sorry?
We can have a polynomial verifier for every problem in P just by solving the problem.
Yeah, I have an algorithm to solve the problem in polynomial time, right? I don't need your proof. My verifier will just do its own work and say yes or no, right? The proof can be completely empty, right? And it can, right? Okay? I mean, the verifier is simply something that will basically solve the problem itself efficiently, and you completely ignore the proof, right? Yeah? We are relaxing the problem. NP is saying, you know, we are asking for less from NP than a polynomial term, right? It's only a verifier, right? For P, I already have a deterministic verifier. It will give an instance, it will solve it itself in polynomial time. So every problem in P is also in NP. Okay? Yeah? Questions about that? Okay. Okay. The next observation is that what is exponential time? Let's define exponential time to be the set of all problems, or the class X is a set of all problems that have an algorithm that runs correctly in time that is exponential in the input length. Okay? Is SAT in exponential time? Yeah? Why is SAT in exponential time? I can try all possible assignments, right? And check each of them. Yeah? Why is independent set in exponential time? I can try all possible subsets and check if any of them is right. Yeah? Okay. So what is exponential time? Exponential time is simply that, you know, I have an algorithm which runs correctly and takes more time than some fixed exponential in the input length. So I'm even allowing you like something like, you know, 2 to the n to the 100 is also exponential time, right? It's a polynomial in the length, but it's exponential in, right? 2 to the polynomial in the input length, okay? Okay, my next observation is that NP is in exponential time. Every problem in NP is in exponential time. Why is that? Okay, what does it mean that a problem is in NP? It has a polynomial time verifier, right? Okay, with what property? that if it is a yes instance, there is a proof of length which is polynomial in the length of the input such that it will convince the verifier, right? And if it is not a yes instance, no proof of polynomial length will convince it, right? There is a fixed polynomial. So how can I create an exponential time algorithm for you given an NP problem? Okay, here is exponential time algorithm. Take that verifier. Try all possible proofs of length polynomial in the input length and feed it to the verifier, right? What will the verifier do? If there is any correct proof, it will say yes, right? If you run through all the proofs and it says no to everything, what do we know? That it has to be no instance, right? Yeah? So it's like, take SAT. You have a verifier which, given a formula and an assignment, will check whether it is satisfying or not. How many possible assignments are there? Only exponential in the size of the input, right? So for every possible assignment, you run the verifier with that assignment, right? That takes polynomial time, right? Because the verifier is efficient. You run through all assignments. If the verifier says yes to any of them, you say, yeah, this is a yes instance. If at the end of all the proofs, it says no to all of them, it must be a no instance, right? Right? By definition, it must be a no instance. That means this formula is not satisfied. Okay? So for every NP problem, because you have a verifier which, two properties, verifier runs in polynomial time, and second, there is a fixed polynomial such that if the size of the proof to convince the verifier for a yes instance is polynomial in the input length. So the number of proofs you need to enumerate is only exponential in the size of the input instance. Okay? So you can run the verifier on all possible proofs. If at any proof it says yes, you know it is a yes instance. If for all proofs it says no, you know it's a no instance. But the running time of this algorithm is how many proofs do I have to enumerate? 2 to the some fixed polynomial in the length of the input. That depends on the property of the verifier you have. And then you try all possible proofs and run the verifier on all of them, and then if it is yes, you say yes, otherwise no. So I've given you an exponential time algorithm for the problem, right? Okay? So NP is in exp. Okay? So examples. SAT is try all possible assignments, independent set is try all possible subsets thing, and so on, right? So what do we know? P is in NP is in exp. Okay? Big question, right? You know, what is the truth? Right? Where is NP, right? You know, is it equal to P or is it equal to, is it closer to exp, right? Okay? Okay. Okay, you know, why do we care about NP? Because many problems we want to solve are in NP and we don't know how to solve them, right? And we would like to know. Okay, many things will go wrong if in fact P equal to NP, right? You know, you can break crypto systems and, okay. This last part is something that you can solve homework, right? You don't have to, so suppose P equal to NP, what does it mean, right? It means there is an efficient algorithm which will check whether something is true or false, right? So you can, I can create, if P equal to NP, I have an efficient algorithm which if you give any homework problem will generate a proof if there exists one easily. So then you can just, we'll be out of business, right? You know, in the following sense, right? You know, you can buy that software and you feed it homework problem in some sufficiently complex but formal language, it will spit out. If there is a short proof, it will spit out whether it is a short proof or not. No, this may look facile, but you know, to understand it properly or think about logic a little bit. But let me not. Okay. Okay. This I'll come back to, but let me define NP completeness, and then we'll come back to. Okay. So NP is a class of problems, right? What does it mean it's a class of problems? All these problems we want to solve are, we don't know how to solve them efficiently, but they are in the class NP. So then you say, okay, what should how should I think about these problems, right? Now you may say, is there some notion that this is the hardest problem in NP? Right? This is the hardest problem in NP. What does it mean? Can we define it formally? And let's think of the following definition. A problem X is said to be NP complete. Well, it should be in NP. Okay. So it should be the hardest problem. What does it mean it's the hardest problem? If I solve this in polynomial time, I can solve everything in NP in polynomial time. Okay, that's a notion, that's a good robust notion, right, of the hardest problem in a class. Okay, right? So it's saying something like this, right? Look, I have a class of problems NP, and I found one problem X such that if I solve this efficiently in polynomial time, everything in NP can be solved efficiently in polynomial time. Okay, that would clearly indicate that it's a special problem, right? Because if I solve this efficiently, everything will be solved, so it must be a special problem, right? So we'll call it a special problem, and instead of calling it a special problem, we'll call it a complete problem, right? Okay, okay. Complete means what? It can basically effectively collapse everything into itself, right? Okay, so that is the notion. For any y in NP, that means if you look at any problem in NP, it can be reduced to this problem, right? So X is at least as hard as any other problem in NP. So the first question is, so very easy. If X is NP complete, then X can be solved in polynomial time if and only if P equal to NP. Why is that? Well, if P equal to NP, clearly everything can be solved in polynomial time in NP, right? Okay, that's easy. But if X is an NP complete problem, then it means what? If I solve X in polynomial time, everything can be solved in polynomial time, right? But converse is also true. If there is some problem that is not solvable in polynomial time, X cannot also be solved in polynomial time, right? Yeah, because if X can be solved in polynomial time, everything can be solved in polynomial time. So if there is any problem which is not solvable in polynomial time, then X must be in that class, right? So that's what it means, that if X is NP complete, it's saying, aha, you better not think that you will solve this problem in polynomial time unless the whole class collapses into P. Okay? Okay. The natural question is there any problem which is NP complete? Right? Let me say, right, So maybe there is no problem which is NP complete, right? Why should you believe that there is a problem that is NP complete? It's not obvious that there should be a problem that is NP complete. Okay? But there is one, and in fact many problems are NP complete, and in particular SAT is NP complete. Okay? This is the famous proof of Cook and Levin, right? That SAT is NP complete. So what it means is that if you can solve SAT in polynomial time, all these problems in NP can be solved in polynomial time. Okay? So you should wonder, how can I even prove that? Right? Right? What does it mean to prove it, right? Like, wait a second, there are infinite number of problems in NP. So how can I prove that every problem in NP reduces to SAT? That doesn't seem to make sense, right? Because I have to say, oh, this reduces to a SAT, this reduces to SAT. Oh, but I will never finish, right? Right? So you can't prove it like that, right? You have to prove it simultaneously. Okay? What does it mean, right? You have to give a meta proof, right? So that's why logic is important, right? Why that's why SAT is the seed problem. Why SAT? Why did they prove it's SAT and not like independent set? Because SAT itself is a meta problem, right? So it makes sense that you say, I have to give an abstract proof that simultaneously applies to all problems in NP, okay? And that's Cook-Levin. It's not actually a hard proof, but to prove it, you have to go through Turing machines. It's much harder to prove it with the certifier notion. It's much easier to prove it with Turing machines because Turing machines are so simple, you can actually see all the details. If you try to prove it with this, then you get into a little bit of complicated, what is an algorithm, right? That's not very formal. So this is not a hard theorem in some retrospect, but it is an important, obviously, theorem. Okay. So once you have that some problem is NP complete, you can use reductions to prove many other problems are NP complete. Why? Because if SAT reduces to some other problem which is an NP, then by transitivity of reductions, everything reduces to that problem too. So that's also NP complete, right? And so how do you prove something is NP complete? First you have to show that problem is in NP, right? Okay. And then you have to show that some existing NP complete problem reduces to it in polynomial time. Okay? Alright? That's what you need to do, right? And here is what you see, here is the list, right? SAT is NP complete. Cook and Levin proved it for us, right? We don't have to do the hard work, right? They first gave a seed, right? SAT is NP complete, right? And we saw that SAT reduces to 3 SAT, right? And 3 SAT is in NP, so 3 SAT is NP complete, right? Because we already know SAT is NP complete. Well, we saw 3 SAT reduces to independent set, which is also in NP and has independent set is NP complete. We saw that clique is NP complete because independent set reduces to clique. We already saw that. And vertex cover reduces to, independent set reduces to vertex cover, so vertex cover is NP complete. Vertex cover reduces to set cover, so set cover is NP complete. Hamiltonian cycle is NP complete. We didn't prove that, I'll prove it next lecture. Okay. 3 coloring is NP complete. That's also not obvious, it's a very beautiful proof. We'll see that again next lecture. Okay. That also comes from 3 SAT to Hamiltonian cycle, 3 SAT to 3 color. Okay. It's very important to reduce, to prove a new problem is NP complete, you have to start with an existing problem that is NP complete and reduce it to your problem, not the other way. Okay. It's very important to know the direction, right? Okay. It's always easy to reduce a problem to a harder problem, right? That won't tell us anything. It's good. It helps us design algorithms, right? If you can reduce our problem to shortest path problem, we know how to solve shortest path, so we get an algorithm. But if you want to prove something is hard, you have to prove an existing hard problem reduces to your problem. Okay? The direction gets flipped in algorithms versus hardness, right? So you have to be careful about that. Okay? And let me tell you one interesting problem, which is not problem. We saw this, so let me go back to this, right? Which is again brings back the notion of NP. I call it, is linear programming in NP? Why is linear programming in NP? We all said, linear programming is in P, right? But we are not going to tell you the algorithm. But let's even try to understand, why is it in NP? What does it mean it is in NP? That means it must have a certifier and a solution. If it gives me the solution, I can check that solution, right? Okay. So what is the LP problem? I have the following problem, right? What is it? I give you, I have say this standard form, max Cx, Ax less than equal to B. Okay, well as a decision problem, what is the problem? I give you this C, A and B and also some number and I say, is there an optimum solution? Is there a feasible solution of value at least K? Right? That is a decision version of LP. Okay, how can I convince you that there is a solution of value at least K? Easy, right? I give you a solution, right? Okay, I give you x1, x2, x3, x star is a solution or y is a solution and you will say, is it satisfying all the inequalities? Okay, good, it is feasible, right? Is it satisfying at least the value is at least K? Good. C1 plus x1 plus C2 x2 plus C3 x3 plus Cn xn is greater than or equal to K. Happy, right? It's an NP. No, not so fast, okay? There's one more part of the NP definition that's important, okay? What is it? The size of the, right, the length of the solution, okay? How big are the numbers x1, x2, xn that I give you, okay? Maybe they need huge number of bits, okay? Any feasible solution may need a huge number of bits, right? How do you know that there is a solution which is not too long compared to the initial numbers? Okay? The problem is not in the verification, it's trivial, right? If you know the numbers, you just check it is feasible and check whether its value is at least given number K. But how do you know there exists a solution whose bit length is not too much bigger than the initial input length? Okay? It's not obvious, no? Now numbers are involved, right? How do you know there is a short proof? When I say linear programming is in P, you never asked me, okay, the most basic thing you need to ask is, how can the optimum solution size be polynomial in the input length? Even if the inputs are all integers, how do you know that the number is actually a rational number? Why should it be a rational number even? Maybe it's a real number, right? I can't specify a real number, okay? It's not obvious, no? You never asked me that question, okay? Okay, so it's not even obvious that it's in NP, okay? Okay, but it is in NP, okay? Let me quickly prove it to you. using some hand waving thing, you can check the notes. The important property of LP is that if there is an optimum solution, we know that there is a vertex solution, no? Right? What is a vertex solution? So I don't have to give you an arbitrary solution, I can give you a vertex solution. How do you specify a vertex solution? As a solution of a linear system A prime x equal to B prime, where A prime x equal to B prime is a set of hyperplanes that define that vertex, right? A full rank system. Okay? Does that make sense? Right? Okay. So what is the solution of a linear system? It is the inverse of that matrix, no? Times B. Okay, now, okay, what is the formula for the inverse? 1 over the determinant of the matrix times the adjoint of the matrix, right? Transpose times B prime, right? So you have to tell me that, why this solution has bit complexity that is polynomial in the initial numbers. And it is not obvious, okay? And for that, you have to say, the main problem is how big can the determinant get, okay? And you go and say, aha, what is the determinant? The determinant you can write as this formula, which is this exponential number of terms in the determinant, right? I won't go through it, but you can check when you go back home that the determinant has a formula, and from the formula you can conclude that the number of bits you need to write down the determinant is polynomial in n and the initial numbers that I gave you. Okay? So that's how you convince yourself that there is a solution which is of length that is polynomial in the initial input length. To even convince yourself that it's in NP, you have to do this exercise. Forget it in P. Okay? So you think this is complicated. Integer programming is even worse because the optimal solution doesn't have to be even a vertex. But even that is in NP, but you need advanced geometry to prove that integer programming is in NP. So here the issue is not verification, okay? Verification is easy because you can give a solution, it is trivial to verify something. The issue is how many bits or what is the length of the proof that you need to give me to convince you that it's actually feasible, there exists a feasible solution of complexity polynomial in the initial input. That is not obvious for some problems. It is obvious for problems like SAT, but it's not obvious for all problems. Okay? Okay. All right.